Some charts are flawless, but lawless. They're beautiful on the surface, but underneath, they violate core statistical properties. Now, what does that exactly mean? Well, let's create an SPC chart that looks too good to be true. I've got a set of data. It comes from three different machines, and I'm going to go and create an X bar and R chart. So I've got as my data, I have a value, and I'm going to continue, and then I need a subgroup variable, which is my subgroups. And then I will click continue and continue, and voila. There's an SPC chart that looks too good to be true. And you can see that the values all fall well within the control limits. Nothing is ever getting close. And even on the range chart, everything is hugging the line above and below. And we pat ourselves on the back and we think we've got a great process, but in reality, things are wrong. Now, what in the world could that mean? When I first encountered this sort of phenomena over 30 years ago, it was truly a head scratcher. On that X bar chart, the averages should be randomly distributed within the limits. Clearly, it's not. So I thought the limits have to be calculated wrong. So I did the calculations manually myself. The limits were actually correct. But it looks wrong. Nothing that is that good happens at random. How can that possibly be? And then I figured it out. Now, when you first learned SPC, your instructor spoke about a boring concept called rational subgrouping. You were busy snoozing at this point, grabbing an energy bar, or looking at email. Lots of statistical gobbledygook. Rational subgrouping simply means that all of the values in a subgroup come from the same population. And when I dug in deep, that wasn't the case. In this particular example that I had, each value in the subgroup came from three different machines. They had averaged those together and taken the range of max minus min. Lo and behold, there were biases between the three machines. This results in a constant average bias in the range chart. Because the average range is higher, the limits on the average are wider. So let's look at my SPC example here. Let's plot out a trend chart of those three variables. So we can go, we'll just do a trend chart. And we will grab sample number one and sample number two and sample number three. And we'll click continue and continue and continue. I'm going to not turn on the labels. And what do we have? So this pale blue line or blue-gray line is sample number three. And we see that this orange one is sample number two. And your eyeballs can see in almost every case, a couple of examples, there is a consistent bias. And rational subgrouping would tell us that these points should go above and below each other randomly, and that clearly is not the case. So biases matter if you're trying to subgroup them together. And my guess is you might have something like that in your facility that looks like this. So the only way the chart ever goes out of control is something truly catastrophic happens. With the range chart, with a subgroup of three, you should actually see a lot of small range values. In theory, zero is possible. So how do you solve this? You either apply an X moving range chart to each of the three machines, or you fix the machines so that they are aligned. Going forward, when you look at an X bar and R chart or an X bar and S chart, you should see both charts somewhat fill up the space between the limits. If the data is too tight, but the limits mathematically check out, you have biases. So be careful out there. The streets are messy, and so is data. But remember, there is always a way.